Stokes Theorem, generalization of Green's theorem. In a lot of ways it looks like Green's theorem, and we'll make a closer connection right here. It simply says that the integral over a surface of the curl of f dot the vector ds, d capital S, where d capital S is just the normal times the surface area, the area of the surface increment, is equal to the integral around the boundary, the closed integral around the boundary of this region, surface, of f dot t dr, which we write as f dot d vector r. So this and this have to be equal, among other things. Tells you that if you can't integrate this, you can still integrate it if you can integrate this. Okay? And if you can't find this, can't do the integration, you can still get it integrated by integrating this, because these are things that are going to be equal. Now, this is the integral of the curl of a function, is its total circulation over the surface. This is a circulation around its boundary, circulation of the vector field. We've talked about that fairly extensively. A lot of hand waving, some pictures on the board. Okay, so these two are equal. Now, this is a whole lot like Green's theorem. If you have a plane region R, let's think in the xy plane, so that you have a function f, vector function f of xy, and you got a boundary curve here. Remember, Green's theorem says that the integral of, I'm going to make that a dr, of f with respect to r. I use ds, which is okay, but just to be consistent, I'm going to use a dr. The integral over the boundary of the tangential component of f, again, we've talked about that, hopefully we understand what that means. The f dot t dr, which could also be expressed, as we say, as f dot dr, and this is the expression we'll actually use. Okay, well, this is the actual expression for Green's theorem for any surface. Okay, because the plane can be regarded, the xy plane can be regarded as part of three-dimensional space. It just happens to be the part that's in the two-dimensional plane here. Remember, Stokes' theorem is going to apply to any surface, any orientable surface in three-dimensional space, any orientable surface with a boundary. Okay, well, by Green's theorem, that, as we've seen, is equal to del cross f dot n with respect to area. Well, that's this, okay? In the plane, we're saying that that's equal to del cross f dot k times the area increment in the plane region. So this would be over the region R. This integral is over the region D, a parameter domain where ds is in terms of the parameter, and actually it's probably not a good idea because I should have my cross product of the tangent vectors, so I'm just going to change that to R and cross out this. Note that that's a parameter domain. Although you would parameterize a surface in general, you don't have to when the surface is in the plane. It's already essentially parameterized. Anyhow, this is going to be equal to this. This is in the plane. That's just Green's theorem. So the Stokes theorem reduces to Green's theorem if you're in the plane. Okay? Just as when we proved Green's theorem, we could break our region enclosed within the boundary, our plane region R, into little rectangles, with the exception of those rectangles that would intersect the boundary, in which case we have something that's three sides of a rectangle but truncated by this boundary. When we do the circulation here, integrate the circulation around here, and the circulation around here, circulation around here, circulation here, and circulation here and here, on all 7 of these regions, but 6 of them, I guess. What happens is, on a boundary that's shared by 2 adjacent regions, we're going to be integrating in one direction for one of the regions, and in the other direction on this boundary for the other region, and everything essentially just cancels out. Okay, the integral just cancels out. So over the whole interior of the region, this happens, with the exception of those little regions that have one side along the boundary of the whole region. In that case, we still have cancellation on all the white segments that I've drawn here, but on these blue segments, there's nothing to cancel it, so we're just left with the integral over these blue segments, and left, in this case, with a circulation around these blue segments. Now, whatever your vector field is, your vector field, this is not a vector. This arrow represents the direction of integration, but you would have a vector field then, maybe a vector field like this and like this, perhaps with a component in the direction of this segment or this segment, and also a direction normal to the segment. Okay. Again, we talked about that. I don't want to say too much about that. But what I really want to say is, now if you have a surface in 2 dimensions, or 3 dimensions, that has a boundary, so it's like you got this windsock, or this bag here, or whatever this is, with an open end here. Well, the open end is your boundary, and this is the rest of the surface. You can break this surface into little pieces like these, and on each piece you can integrate. So you can, let's see, you're going this way, so you're going to go this way. So you're going to, yeah, you're going to, depending on your orientation, you're going to do the same thing here that you did on the little rectangles. And conceptually, at least, intuitively, we can see how circulation around one rectangle is canceled by the circulation on the adjacent rectangles, okay? Just take this little rectangle, it's not a rectangle, but this little piece of area, and then you're going to have circulation around here, which is going to give you circulation in the opposite direction, so you have circulation both directions along this side, and then you've got this one here, and again you have circulation in both directions around this one, and then the same thing around this one. And around this one up here. And every one of the 4 sides of this region is ultimately, if you add all the contributions of the little regions, is every side, I don't remember the rest of my sentence, the rest of them, every side of this thing is then going to be integrated in 2 different directions, giving you equal and opposite results. And all that adds up to 0, except up here on the boundary. So these blue shaded regions intersect the boundary, and everything cancels, except the part on the boundary, just like it did down here. Now there are tricky things you got to worry about, because you can't break this surface into rectangles. Okay, you can parameterize it, and you can have rectangles in your parameter space, and there are all kinds of things that you can do, but some of them are a little too advanced for this course, so we can't do a rigorous proof of Stokes theorem. We do an intuitive argument, which I've just done. We can even make it a little more rigorous if this surface is the is part of the graph of a function of two variables, vector function of two variables, an f of x, y. And your text does that. I'm not going to have time to do it. But it's an interesting proof, and I do recommend it to you. Okay, it's not that difficult. The ultimate proof is quite a bit more advanced, or at least you kind of need advanced calculus at least. So we're not going to even talk much about that, except to say that there is a proof. Okay, well that's what Stokes' theorem says. We're going to work through one example in a lot of detail. That's all we had time to do in class, because we're going to go through it in good detail. So let your function, let f be this function. Now it's a function of three variables, because now we're in three dimensions. With Green's theorem, you could only have a function of two variables. Now we've got a function of three variables. There's your function. And let r be, well, r is going to be, I sketched it somewhere. I thought I had it here. Hang on a minute. Gee, I had a really pretty picture of it. You know what? No, that's not it. Okay. Okay, this is where I started. I'm sorry. Confused about what's on which board and what I did when. I thought that I had a sketch here, but I've got a sketch on the back of this board. Okay. Let's just let f be this, and let r equal to 3 sine theta, 3 sine phi cosine theta I plus 3 sine phi cosine theta j. And this cosine here should be a sine. Can you see why that's all we had time for? Okay, I think I was in better shape this morning. We'll see. Okay, here's an r vector. That's a parameterization of a surface. You can figure out what the surface is easily enough. These being spherical coordinates, that's just the x in spherical coordinates, that's just y in spherical coordinates, and that's your j vector in spherical coordinates. And I think on that cosine theta, I need to have a 3. I think I used it. Pretty sure I used it. Okay. This is going to be parameterization. If you do it for theta from 0 to 2 pi and phi from 0 to pi, that's just a parameterization of a sphere of radius 3. Okay? This is a sphere of radius 3, but in this case, theta is going to go from pi over 4 to 3 pi over 4. Phi is going to go just from 0 to pi over 2, and we'll see that that's just a part of the sphere that's like halfway through the first octant through halfway through the second octant. It's a 90-degree segment of the sphere above the xy plane. We'll see how that works. But there's a parameterization. Just going to demonstrate Stokes' theorem. Okay, then in the xy plane, we're going to have a path that consists of three segments, a C1, C2, C3. It's like a pie-shaped, it's a pretty good size shape, a piece of pie, it's a quarter of a pie. A pie-shaped path, or at least the outline of the pie, the boundary of the pie, slice of pie. Okay, that's going to be our path. And we'll see how that works out in 3 dimensions. But here is definition of this path. R1 is going to be Ti plus Tj, so that it's T is your X, T is your Y. So your X equals your Y, so you're moving along this line, and you're moving from T equals 0 to T equals the square root of 3, so this point will be square root of 3, square root of 3, okay, according to this. So this point is and you can easily verify that since the X equals the Y, you're moving along this line. If T is 0, of course you're at the origin, so that this is a parameterization of a segment from the origin out to the point square root of 3, square root of 3. Magnitude of this, or the distance from here to here, is going to be the sum of the squares, square root of the sum of the squares of this thing. Oh boy, I did something real bonehead here. Should be the square root of 3. Because what I just said contradicted what I did. Should be 3 square root of 2. Okay, I'm going to fix that before we go on. But what we've got here, it is at least intended to be a parameterization of this and then this. This is an arc of the circle between theta equals pi over 4 and theta equals 3 pi over 4. That arc is going to be 3 cosine theta I plus 3 sine theta j, from pi over 4 to 3 pi over 4. I'm going to have to look at this and fix a few things. Okay, I'm going to fix these things and then we're going to go on.